Hello, this is Jonathan Medina with his unit testing presentation. The date is May 13th, 2025, and this is for Professor Park. Now, before I start with this presentation, I would like to say that this was not an opportunity. In fact, this was a very unfair assignment that I do not believe was justified for this class. I did not have fun with this assignment, and I don't believe I should be having fun, but either way, this was an assignment that was just completely unfair. Anyways, moving on to the presentation itself. I would like to start with explaining what unit testing is. Unit testing is a form of software testing by which source code gets isolated to validate certain behaviors. Now, to properly enunciate this point, unit testing is basically deciding what part of the source code is a unit and must be isolated in order to properly test out each piece of the code and get a specific behavior returned. Now, all of this is something that my apologies. This is something that I will dive more deeper into as my presentation goes on. Anyways, to continue with the slide, this is not like integration testing, which has multiple parts of the code and software tested as a group. So for example, let's say you have a assembly line for a car and you had to test certain parts of the code to not the code, let's say of the car at the same time. Let's say you need to test the axles and the wheels, but you didn't want to test each one of these individually. You would have to test both of them as a group at the same time. And going against this as well, this is not like system testing, where system tests are run by the compiled software. Going back to the car assembly line analogy, this means that system testing would be equivalent to the car producer producing one car and then taking that same car, going outside with it, and then testing it out into a field to make sure all of its functions are working well. In fact, since our current topic is about unit testing can be used as a component of acceptance testing, which is another system level testing as the same thing as system testing, where the code in its entirety gets tested to ensure that the entire software meets within users' expectations. Now then, on the left side, we can see that the unit test cycles have 5 main parts to its life cycle. The first thing, it checks out the code from the repository. In other words, it checks out where has it been implemented in each piece of code, in each source code, and then it goes through it, combs through it, and makes sure and sees where its dependency has been injected into each class to ensure testing. Afterwards, it makes changes, not the code itself. The developer must make changes based on the results that has been given by the unit test. Then the unit test gets executed. Then it has to fix its then afterwards the developers have to fix its defects and re-execute the unit test. Afterwards you have to review the code. And then lastly, you will have to check it into code repository. But for the sake of this presentation, I have narrowed it down into 3 separate stages. The first stage of unit testing would be the scenario test. This is the most basic and I would say actually more complicated way to test source code. In scenario tests, basically what the developer does, they take the whole app and they test it by pretending to be a user in this test. The second stage, in case if the scenario test does not work, would be functional tests. And functional tests would be involving testing not the app, but the subsystem of the apps that relies on external dependencies. So instead of testing the whole app and going in as a user, you would be testing the subsystem instead for its external dependencies and anything involving the subsystem. And then finally, and lastly but not least, is the unit test, which is the final stage. Now, this is the main part of the presentation and what we are focusing on. And unit tests by themselves focuses on testing all individual classes in isolation. So, to put these 3 stages into the car manufacturing scenario, stage 1 would be developing the whole car, assembling it, then taking the car itself into a field and then testing the whole thing by pretending to be an average user. Stage 2 in this car analogy would be taking, I would say, functional parts of the car itself, let's say like the wheels, axle, the engine, the car seats, heating, AC, and checking to see if everything is working well based on its external dependencies, which would be the car battery. And then finally, stage 3, the unit test itself, where instead of taking all these components that relies on dependencies or the car itself, in my car analogy, this would be just testing out every single part of the car itself in isolation. Excuse me. So this would be like taking the wheels, spinning it, aligning it, ensuring that the bearing of the wheel or like the hub of the wheel actually spins. Same thing with the axles, making sure that it's structurally sound. Is basically breaking down the car into its most minimal parts and ensuring that each one of these parts are working correctly. Now then, between all the stages that I have laid out, what is the most preferable stage? Now, stage 1 scenario tests. Honestly, they are too time consuming and very unreliable. Even if the strengths of scenarios tests are high confidence paths, which means that each time you run this test, you will be absolutely confident in the path it took within the source code. This will be required, I'm sorry, this will still require a debugger and will be hard to reproduce failures. Sorry. Now, to highlight this of the pros and cons, once again, even if you are running through the code as a user and checking it out yourself, you can have high confidence that whatever you tested out will work. But you would have to have a second opinion, which would be the debugger. And even then, who knows if they could reproduce the same failures that they have arrived at. Moving on from scenario tests, functional tests can stimulate conditions that were not possible in scenario tests, but they also require external dependencies and a debugger. So functional tests have an advantage over scenario tests where they have been pre-programmed with conditions that probably could not have been programmed in scenario tests while the developer or the debugger has been testing the code as a user. But the issue within this is that this requires external dependencies, which means that if the setting of the PC does not match what the code needs, then it might not work. And this also requires a debugger, which has the same issues as scenario tests, where it would be hard to reproduce the failures. Now, finally, we move on to unit tests. And unit tests are tests that are only applied to individual classes and can simulate all error conditions. Alongside with this, developers can continuously run these unit tests after each file modification as well. So with unit tests, you have the advantages of functional tests, where they can simulate the error conditions that were not possible in scenario tests, like functional tests. But unlike functional tests, they only test the individual classes. Henceforth, we shall be referring to these classes as units. So it takes a unit, isolates it, tests it, and reproduces an error if there is one within the test. So developers can continuously actually run these after each file modification. So these are continuously running, automated, and very efficient. Now, obviously, judging from comparing and contrasting these three stages of unit tests, the most time efficient and reliable stage of testing, due to its abilities to be utilized without a debugger and knowing which part of the source code went wrong, would be unit tests. I'm sorry, I will need to take the slide out, but I will move it in the final slides because this is a double slide. Moving on. The characteristics of unit tests. They have three main characteristics that make them the most ideal form of testing. Assertions, automated testings, and exceptions. Now, assertions are methods used in unit testing dependencies such as JUnit, which is a Java based uh, unit testing dependency, or Mockito, which also follows the same framework as JUnit. They are normally called with methods such as assert equals, assert false, assert not null, assert null, assert same, and assert true. All of these are methods within these unit testing dependencies that are usually followed with the syntax within the parentheses of the expected results of the assertion, and then a comma, and followed by the actual result of the assertion. So let's say, for example, assert false. Within the parentheses, you would have to write false because that's your expected result first. And then afterwards, you will need to go into true in case if the code actually returns true instead of false, which would be an error. Also, moving on, automated testing can be run by unit tests without human interference, in the way of speaking that this can cause unintended side effects. So, once again, moving back to the earlier slides, this is why it was highlighting the fact that unit testing does not need a debugger to also test the codes, because debuggers are human, and humans can cause unintended side effects within code, which can lead to things becoming more error prone, even code that was not actually functioning being labeled as functioning and then moving on. And finally, we have exceptions, and they are crucial when it comes to unit testing classes, because exceptions needs to be handled in a way of when you are testing the class, and especially if you have a class that's dependent on other factors. Let's take in, for example, the list array. Let's say you have a list of an array that has 23 objects, but the array that in this class returns 24. So, in case of that happening, then it should catch the exception within the unit test and play it back in case if you were expecting that the exception to happen. And if it didn't, then it will just automatically fail the test because you did not specify that you wanted an exception to be played during this portion of code. Now, moving on again, what goes into a unit test? Usually, good and reliable unit tests are done with mock objects and mock classes. Both the mock objects and classes are pre-programmed objects and classes, with the exceptions from which form of the calls they are expected to receive. Now, to more articulate this, mock objects and classes are objects that and classes that are basically pre-programmed with pieces of code that has certain expectations to it. And basically they are not they are similar but not entirely like the real objects. So in this case, let's take a warehouse for example. In a warehouse, you would say you have a warehouse and packages, right? But for the sake of unit testing that's using a mock object, we shall make a mock warehouse which has the same functionality as a real warehouse, but it is not the actual warehouse itself. It's only used for testing purposes. And in fact, these mod objects are the only form of double objects which are double objects are just basically objects that are copying one set of code. If you'll excuse me a second. They are pretend objects that are used in place of real objects for testing purposes. So, that is the definition of double objects. Going back to the slide, mock objects are the only kind of double objects to insist upon behavior verification instead of state verification. And going on, this is opposed to stub objects that can do the same behavior as mock objects but have major differences that we shall go into the next slide. Mocks versus stubs. Stub objects are similar to mock objects in the fact that they are simplified substitutes for a real object that can provide a controlled and predictable environment. Now, that's where the similarities end, because mock objects are not controlled and predictable. They are just imitations of a real object. Now, mock objects are objects that imitates a production object in a limited way. So, unlike a stub objects that are being used as a substitute for a real object in a controlled and predictable environment, mock objects are just imitations with limited capacity, and they are not supposed to be used as substitutes for the real object. They are its own thing that's only being used for testing purposes. Now, stub objects are usually reliant on state verification in order to check if the class worked correctly on a system-wide level. And state verification are basically a verification that is returning if the class itself or the code itself worked as intended on a system-wide level. For the car analogy, this would just be taking, like, once again, the actual motor, wheel, and engine. Taking the whole system of the car, actually, and just checking to see if the car runs, moves, and drives. Now, this is in contrast to mock objects, which insists on behavior verification, which are more isolated, and they actually check to see if the order of the source code made the correct calls. So, in this case, in our car analogy, this would be like going to make sure that the car has fuel. If the fuel is running through the car, if the fuel is getting to the engine, if the engine runs, if the engine is producing enough powers to spin the wheels and the gears in the transmission, and ensuring every individual part that's supposed to go into this class works as intended. Moving on, overall, mock objects are worth trying when the test-driven development of the developers are to tell when both something goes wrong. So once again, in the car analogy, let's say the wheels gets a flat, so you can tell if the wheels are at fault, or if something else went wrong that doesn't let your car run. And it also tells you what exactly went wrong within the class that it's being tested. So once again, with the car analogy, this would be like getting a flat tire, and if you're using a stub object, as the stubbed object would tell you that the car itself is not working and you would need to replace the car. If it was a mock object with mock wheels, then if one of the wheels fails, then you would be not only able to tell that the car itself actually is fine, but you'll be able to tell what wheel actually got a flat tire and what exactly went wrong with the class or with the car for it to lead up to this point. Now, in my previous slide, I mentioned that there is test-driven development, and I wanted to take the moment to talk about test-driven development. It is a way of development that is the most preferred way, and it is broken down into 3 simplified steps. Basically, we are writing a test for the mock version of the produced code that's going to be added, which means that this starts by writing a simplified version, not simplified version, a imitation of the source object or the unit to be tested, and separately to be isolated. And then afterwards, we have to write the functional code and write the test until it passes. So this means we have to continue writing the code and then placing it into the test, writing the test, and then using the test until it passes. So which would be your red. So you need to continue writing a failing tests over and over again until it actually turns green, and then it actually passes the test. And then when it does, it can be refactored into the source code, and then you can repeat this process in order to implement it and update the class as the developer is learning about the bugs. Now, the reason why this is preferred is that this can reduce bug density and encourage more modular designs while reducing code complexity. Now then, why should you bother with test-driven development in the first place? Unit tests as a whole can give a more insightful and clearer perspective into visualizing and finalizing the API design, which means unit tests can help developers easily visualize the final product more easily and share it to stakeholders and users. Well organized and detailed test descriptions enshrouded in code can be easily implemented for a future requirement, which means each time that you run a test, of course, you can't have the residual test stay within the code, but if you organize the results, keep it enshrouded in code, and then have it as a comment, that could be implemented later and more easily for a future requirement or a future behavior. It also enables developers to understand the problem enough to articulate it in code. So if there is an issue with the code or with the user, or if something happens, then they can go back to the problem, understand it, what went wrong, and then are able to digest the problem with code and see how they can fix it. Also, it helps with quality assurance by making it an automated process as opposed to having it be done by a human that can also lead to errors. Once again, going to my first few slides, like having a debugger, and that can lead into unintended side effects. Then finally, this having an automated quality assurance ensures the opportunity for automatically preventing any possible broken builds from being deployed into production. So having this automatically running every single time, eventually, or not eventually, lowers the risk of any broken code being deployed into the finalized production. Moving on, what exactly makes a good unit test? A good unit test has numerous but distinct functions that should all contribute to answering these 5 important questions. What are you testing? What should it do? What is the actual output? What is the expected output? And how can the test be reproduced? So, if there isn't an answer for the first 2 questions, then it doesn't matter what you get for the rest of the questions. No matter what, it is not considered a real unit test and will be nothing but a half-baked and sloppy test that will not return any real results. Good unit tests should be automated they should be automated, thorough, with running through all the paths of the codes, and repeatable with returning the same results with uncontrolled parameters. So basically, this means it should not only be animated, it should not only be automated, but should be thorough. It should be running through every single bit of code. It should also be repeatable, and they should return the same results each and every time without any user input. And then finally, this should also assert the results of your code in tests and even edge cases with different ranges of data. But most importantly, out of all of this, a good unit test should be independent and test one class or unit at a time to be able to pinpoint the location of the problem. These tests shouldn't also rely on each other in case if the first test fails, we can avoid the other tests that are depending on the initial test from failing too. And finally, they should be professional, with the mock code being written out with the same diligence and consistency that is followed in these basics of well-written code. This will ensure that the developer can always read the code easily and fix an issue as needed. Alongside with the aforementioned characteristics, good unit tests should be fast, and anything longer than half a second needs to be rewritten and worked on to ensure minimal risk of something breaking, especially when the code is being coded by more than one collaborator. Finally, how can we use unit testing exactly in Java? Unit tests can be run in Java by using the JUnit dependency in coding. JUnit is the most reliable way of software testing via dependency injections and returning reliable assertions from an individual class were implemented. Tests are usually denoted and started with the @test tag provided by the JUnit dependency. The part that we shall focus on in these slides are the use of assertions, which is the unit testing's primary and only goal at the end of testing. Assertions can be called into Java by importing them within the following code, which I have attached into the code. I will not be repeating them because, well, it's being able to be read over there. Assertions are then utilized in classes as in the following example code provided by JUnit 5 documentation. And in the example above, we can already see that the function assume true will only return true if the actual value is true. However, if it fails, then it will return false to let the developer know that something went wrong, because this should be able to return true because that is the actual result of the assumption. But if the assumption is not correct, then it will return false because that is the expected in case if something goes wrong. Finally, I would like to highlight the importance of assertions. Assertions are important in the matter of speaking that they show and continue to emphasize the result of the isolated class rather than the source code itself, which means this makes fixing code that is non-functional easier, as they can catch their error encoding in the moment that it is called upon in the source code, and can either return red, which means the code still needs to be worked on, as proven in the test-driven development, or green, where the code has passed and is ready to be refactored into the class, and then have the next unit test move on to the next unit afterwards. Finally, assertions are essentially the results of what mockist developers, which are developers that are using unit testing not with stubs or any other double objects, but with mock objects, are mainly focusing on when using such things, such as small classes and objects. So that concludes my presentation, and here are the works cited that I used for my presentation. Thank you for watching my presentation, and I hope you have a great night.